right, here we go. So yesterday, let's recall. Here was the picture from yesterday. Triangle, midpoints, bloop, bloop, bloop. And then remember, I made the segment from vertex to midpoint. What's that called again? A median, right? From vertex to midpoint, we call it a median. And then I drew the other ones, and all of them met at one point called the centroid. And we learned that the centroid is 2/3 of the way from vertex to midpoint. Okay? This point's called the centroid right here. Similar idea today, but different. Okay? You got to remember, yesterday we drew from vertex to midpoint. Vertex to midpoint. Okay? Let's erase these last few steps. Now I'm going to make the midpoint of just two of the sides. And I'm going to draw a segment from midpoint to midpoint. Not from vertex to midpoint, from midpoint to midpoint. Okay, this is very important. This segment here is called a mid-segment. Yes? Middle segment, mid-segment. Okay, called a mid-segment. Now, there are two things that are special about this mid-segment. And let me kind of move this around so you can kind of see how it works. All right. There are two things that are special about this mid-segment. Do you see those, Hayden?
Mid-segment and like the bottom.
Yeah.
Like it appears to be parallel.
Don't those always appear to be parallel? That is one of those things. Okay, it's going to be parallel to that third side. Does anyone see a distance relationship that appears to be holding? Yeah, go ahead.
And the mid-segment looks like it would be about 2/3.
Ooh, about 2/3. Well, let's see. Let's see if 2/3 is correct. That's what we used yesterday, right? Let's find distance from D to E. 7.98. No! Stop with the bottle. And then distance from A to C. Oh, what do you think? Is it 2/3? What does it look like? Yeah, about half. All right. Let's make the numbers nice and see if it works exactly. Let's make it 16. Can I do it? Eek. Aha! Did it. 8 and 16. Okay. So there's the second thing. Two things you got to know. Mid-segment, half the length of the third side, and parallel to the third side. Okay. Certainly looks like it's always parallel. Notice as the slope of the bottom side changes, the slope of that mid-segment changes right along with it. Okay, those slopes are the same, so those lines are in fact parallel. All right? Questions? All right, that is the idea of today. You just learned today's lesson in about 5 minutes. That'd be nice. We just do that. Like, there you go. Off you go, do your homework. All right, so 6.4, last section we're doing in this chapter, called the triangle mid-segment theorem. What we just saw is called the triangle mid-segment theorem. Okay. Don't confuse it with yesterday. This is where you will go wrong, right? Because yesterday went vertex to midpoint. They both calculated midpoints. But yesterday was vertex to midpoint. Today is midpoint to midpoint. All right? Make sure you keep that straight. As long as you can keep that straight, you should be pretty good to go, I would say. The objectives, we're going to use mid-segments to solve problems. And then we're going to have, of course, real-life applications of the mid-segment. You'll see it everywhere.
There's no proofs in this section, right? How about this chapter?
Well, I guess, in a way, there's kind of like a coordinate proof today, because we're going to show the triangle mid-segment theorem is true in a specific example, which requires like distance formulas and slopes, that kind of stuff. So
we're just solving it, we're not proving
it. It's kind of like a coordinate proof, which is not as...
I don't remember coordinate proof.
Okay. Well, it won't be that bad. Okay. Here we go. All right, so mid-segment. Now, I only drew in a single mid-segment, right? But if I had found the midpoint of the third side, would you agree that there's 3 different mid segments? Okay. I kind of did M to P, but if I'd found N, this guy exists and this guy exists as well. So this drawing has all 3 mid segments drawn in. A mid segment is just a segment that connects a midpoint of one side to the midpoint of another side. Okay. And since there are 3 sides, we can connect 1 to 2, 1 to 3, and 2 to 3. There are 3 different mid segments. Okay. Now, this triangle in the middle is actually called the mid-segment triangle, MNP. All right. This actually makes a very unique cutting of this triangle. Okay, I'll show you here in a second what's going to go on. But that triangle middle is called the mid-segment triangle. We don't usually learn a lot of theory about it. But I'll show you a neat little idea here in a second. It says the mid-segments of triangle ABC at the right are MP, MN, and NP. Those are the mid-segments. Okay. And then again, that MNP is called the mid-segment triangle. Now, what we just saw in GeoGebra kind of suggested that the mid-segment is half the length of its parallel side, right? So let's look at this real quick. Do you see how AN gets 3 tick marks and NC gets 3 tick marks? How many tick marks should MP get? Yeah. No, 3, right? Because isn't MP half of AC? So if these are both 3, that means that this is the same length as half of this whole side. Okay. So how many tick marks does NP get? 2. And how many tick marks does MN get? What do you notice about all 4 of these triangles? By no, Rickman, never. Are triangles congruent by CPCTC? No. He said they're congruent by CPCTC. Yeah.
No, I said they're
Side, 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 right? All of these triangles have single mark, double mark, triple mark. Single, double, triple, single, double, triple, single, double, triple. Okay? So if you want to break up a triangle into 4 congruent triangles, you draw in all the mid segments. And all 4 of those triangles that you get have to be congruent to one another by side, side, side. That's not really what we're going to talk about today, but just kind of an interesting aside. Like, hey, look, all of those triangles end up being congruent to one another. Okay. Questions about that? All right. So what we're going to do here, this is kind of the coordinate proof that we're going to do today. So here we have a triangle, K, and then the lower left is J, and then the lower right is L. What we're going to do is we're going to go through the process of actually showing that this triangle mid-segment theorem is going to be true first. Okay, we're going to show that MN and JRL, are in fact parallel to each other. It certainly looks like they are. But how would you show that in coordinate proof method? And then we're going to show that MN is half the length of JL. Okay, so we're going to go through and we're going to do these things with coordinates just like you would on the quiz on Thursday. Oh, yes, you will be doing this on Thursday. Okay, distance formula, slope formula, midpoint formula. Great question. All right, so let's first calculate M and N. All right, now I know that the M and N are already drawn in the picture, so in theory you should know what those are. But what if I didn't have them drawn in? You would have to calculate the midpoints first. Taylor. Yes. All right, so help me out here. Who remembers the midpoint formula? We talked about it yesterday. Wolf. Wait, sorry. Finn and wait and Wolf. Wait.
So first I want to find point M, and then you do it like you add up the x's together.
X1 plus X2 over,
To,
comma.
then y1.
Yep.
That's y2. Then y2.
Excellent. Okay. So let's find these midpoints. Make sure, like it looks like M is at -4, 3. I get it, but let's show that. So Finn, help me out Add up the x's and the y's and divide by 2 for point M.
-2 plus -6.
Good. -2 plus -6, or can you say -6
Yeah.
over 2, comma?
5 plus 1.
Excellent. -2 minus 6 is -8. Cut in half is -4. 5 plus 1 is 6. Over 2 is 3. So the point M is, in fact, -4, 3, which is what the picture suggests. No big deal there. Okay. Miss Miller, how about point N? What are my x's here?
-2 and 2.
-2 plus 2 over 2, comma,
5 -1.
5 plus -1 is 5 minus 1 over 2. -2 plus 2 is 0 over 2 is 0. 5 minus 1 is 4 over 2 is 2. Does it look like n is at 0, 2? It does. Okay. But that's good practice to get into. It's nice to know our midpoint formula. Okay. Now we are ready to go. How are we going to show that the two lines MN and JL are parallel? How do we show lines parallel in this class? How do we show lines parallel? Oh, no, no. Runner.
I'm gonna go out on a limb and say you're gonna go find the distance from each and see if it's square.
Nope. 5 letters. 5-letter word. No? Yeah. No. How do you know those lines are parallel? Oh, come on. Yeah.
So alternate interior angle.
Nope, there's no transversal. Yeah. Yeah, the slopes are the same, right? So we're going to have to calculate the slopes here, all right? Now, what's the slope formula? Slope equals y2 minus y1 over x2 minus x1, right? Looks familiar? If you were thinking y equals mx plus b, that's the slope-intercept form of a line, okay? We don't need to do that. We just need to find the slope. So let's find the slope of mn. It's mn, not a w, it's an n. My apologies. Let's go y2 minus y1, 3 minus 2, over -4 minus 0, which is 1 over -4, which is -1/4. That's the slope of mn. Now let's find the slope of JL. One plus 1 over -6 minus 2, which is 2 over -8, which is -1/4. Okay, so these two lines have the same slope, therefore they are parallel. Okay, same slope means they are parallel. MN is parallel to JL. Okay. Questions on that? That's how you find that show that they're parallel, that they have the same slope. All right, now we have to do the distance thing. Okay. So we're going to show that MN is half of JL. So we're going to have to find the distance of both. Okay. So let's find the distance from M to N. That's the square root thing. All right, help me out harder. M to N. Here are the points M and N right here. You remember the distance formula? Square root of the difference of the x squared plus difference in the y squared. Oh boy, help him out. Kaylor, go right ahead.
0.
Yep.
Plus 4.
Yep. 0 plus 4 squared plus.
2.
Yep.
Minus 3.
Well done.
Squared.
Squared. Very good. 0 plus 4 is? squared is 16. 2 minus 3 is -1. Squared is +1. 16 plus 1 is, looks like it's radical 17. All right, looks like it's radical 17. 16 plus 1. Okay. Now let's find the length from J to L. Schrembeck, help me out. 2 plus 6, right? Because it's 2 minus -6. 2 plus 6 squared plus -1. Right? -1 minus 1 squared. 2 plus 6 is? Squared is 64. -1 minus 1 is? -2. Squared is +4, right? And then 64 plus 4 is 68. Okay. Now, that doesn't look right, but we're okay because we have to do the buddy system, right? Isn't 68 4 times 17? And isn't 4 2 times 2? Buddy the 2's. So this ends up being 2 radical 17. Is 2 radical 17 twice as long as radical 17? Absolutely, right? Right? The first one is half the second one. There's radical 17, there's 2 radical 17. So we can say Mn is 1/2 of JL. Okay. That's what the triangle mid-segment theorem does. And this is a good exercise because it requires 2 midpoints, 2 slopes, 2 distances. You're going to be doing this on Thursday. Okay? You're going to be doing it on Thursday. Know your midpoint, know your slope, know your distance.
So it's not really, it wasn't really a proof.
I would call it a coordinate proof.
Well,
What do you mean, like, you're not proving like theorem? You're not like putting.
It wasn't general. It wasn't a general coordinate proof, but it was still a coordinate proof. I mean, you still had to show that the slopes were equal and one distance is half the other.
yeah, that's like solving a problem.
Okay. Well, proofs are solving problems.
Both are confusing.
Okay. Questions? So here's the theorem, formally. Okay. Notice in the theorem they only draw in one mid-segment. That's fine. All right. Sometimes you only have one drawn in. Sometimes you have all 3 drawn in. Okay. But at the end of the day, the mid-segment theorem applies to a mid-segment and the side that it's parallel to, or what we'd sometimes say the third side. Okay. And this theorem says the third side. So the segment connecting the midpoints of 2 sides of a triangle, which in this case is DE, is parallel to the third side and is half as long as that side. We call it the triangle mid-segment theorem. And of course, in some of your homework problems, I would expect to see all 3 mid-segments drawn in which case each mid-segment is half the length of its third side. Okay? Hockenberry.
There's still not a pencil sharpener in here, right?
I have no idea. Pencil sharpener?
No,
Okay.
I have a pencil.
Well, yeah, you can just use it to the other period.
What's this?
Look at Kaler.
Legend.
What this?
He is like the
Oh my
widow who threw in both of the mites
Hey.
that she had. While everyone else was putting in huge bags of money, she put in all she had. Okay. Yes. You gave a pencil.
It was a pick on.
I always pick on you? Oh my goodness. Is that right? A little sensitive, are we? Oh, we are.
What?
Now I'm gonna make fun of how sensitive you are. You used to give me more material.
What?
You used to give me more material.
How's that?
Because now you're always sensitive. I make fun of your sensitivity. You have a journal at home that you write in?
I used to have one, but no, I don't have one anymore. When I was in 3rd grade.
You know, I have a journal. but I think you have diarrhea. You have diarrhea, don't you? Yeah, you do. Peppered with your tears.
Probably cry when I to your wife.
What?
Probably cry
Whoa.
when I to your wife.
Whoa. Now we're getting personal. All right, here we go. So that's the triangle mid-segment theorem. DE is parallel to AC and half of the length of AC. Okay. Of course, in any drawing, you could have all three mid-segments drawn in. All right. So be careful. The mid-segment is always half the length of its third side. Okay. And in general, you expect the mid-segments to all be different in length. Most triangles are scalene. All right. And each mid-segment is going to be half the length of its third side. So generally speaking, you expect the mid-segments to be different. Okay. But again, if the triangle were isosceles, then you'd expect two of the mid-segments to be the same. If the triangle were equilateral, then you'd expect all of the mid-segments to be the same. Okay. Questions here? Let's do some quick examples and we will be done. All right. Take a look at these trusses here. Triangles are used for strength in roof trusses. Okay. In the diagram, UV, kind of highlight here, UV is a mid-segment. Okay. Notice this is the triangle. And VW is a mid-segment. Okay. The question says find the length of UV and find the length of RS. Well, how long does UV have to be here? Bring in the font. What do you think, buddy? How long does UV have to be?
Probably like half of 57.
Nope. I liked your half.
Half of 90.
Half of 90, right? Half of 90. So UV is going to be 45. And RS, what's RS going to be, kids? Yes. There it was. Hockenberry, how long is RS going to be?
114.
Yeah, 114. It's 57 times 2. Okay. Be careful. If I give you the mid-segment, you have to multiply by 2 to get the third side. If I give you the third side, you have to cut it in half to get the mid-segment. Okay. So whatever 57 times 2 is, which is 114, is going to be the length of RS. Thank you, Ricky. That made my day. I'm ready to go now. Questions on example 3. Pretty simple. Pretty simple. Not too bad. All right, let's take a look. Example 4. In the diagram, we're told that AE and BE are congruent, and we're told that AD and CD are congruent. How do I know that CB and DE have to be parallel? Taylor, what do you think?
Because the D is the mid-segment.
That's exactly right. DE has to be the mid-segment, right? Take a look at the information. AE and BE are congruent. So doesn't that mean that E has to be the midpoint? Okay. And then AD and CD are congruent. So doesn't that mean that D has to be a midpoint? All right. And if E and D are the midpoints, doesn't that mean that DE is a mid-segment? Okay. So all we're going to do here is use the mid-segment theorem. Okay. So we're going to say DE is a mid-segment. Okay. By the mid-segment theorem, DE has to be parallel to CB. There you go. Pretty simple. Okay. It gave us enough information to know that DE is in fact a mid-segment. Therefore, the mid-segment theorem applies. And that DE, yep, that's all you have to put.
So how did we get enough information? Just because we know that both sides on are congruent, so it's like.
Okay, so AE and EB are congruent, right? So doesn't that mean that point E is the midpoint?
Yeah.
That side. Same thing over here. AD and DC are congruent, so D has to be a midpoint. Isn't a mid-segment just a segment that connects a midpoint to a midpoint?
Right.
Right? So DE is a mid-segment, and that means that it's half the length of CB and it's parallel to CB.
Okay.
And this one is only asking about the parallel part.
Right.
Okay. So there you go. Not too bad. Questions on 4? Sir,
To use the mid-segment theorem, do you have to have one mid-segment?
at least one. Right. And so in some drawings, like for instance, if point F is the midpoint of this third side, which probably they're implying that it is, but we don't know for sure. If this is the midpoint too, then this would be a mid-segment E to F, and then that would be parallel to AC. Okay. So you could have multiple mid-segment theorems in the same drawing if you have the whole mid-segment triangle drawn. Sir.
Is there a good, like, it's not about this question, but could you use is there a midpoint on the mid segment? Like, could you just keep going forever and ever
Yeah, but if we do the midpoint,
and keep doing the mid segment triangle on each triangle? It
Crazy.
just goes forever.
Wait, I actually have a
And
question.
then stuff.
Well, hold on. So what you're suggesting is this.
Yeah.
Vamonos. Oh, for goodness sakes. So what you're saying is this.
We're gonna play the game of how many triangles can we fit into each triangle.
Is our internet down? Oh, here we go. GeoGebra Classic. Any minute now. Maybe it's GeoGebra that's giving an issue. Okay. Okay, here we go.
I'd say
So what you're saying is find the midpoints of all.
before we do that, I'd say to make things a little more even and crisp, we make it an equilateral triangle.
Okay, I'll just even and crisp is what we're looking for, huh?
Yeah.
Okay. GeoGebra Classic. And I can say regular polygon, but that also means that I can't move the points around to make it not regular. Okay, so let's not make it equilateral. Okay, I think it'll be a better learning experience if we don't. Let's just make it a triangle. Okay, and let's go midpoints. Duke, Duke, Duke. Segment, Duke, Duke. And then are you saying for this mid-segment triangle, find the midpoints of those?
Yeah, and then
Okay.
if you can find make segments of like D to B, then B to E, E to C, that kind of thing.
Yeah. Duke, Duke, Duke. Does it look like it still works?
Just-
Sure does, right? Isn't this guy still, I mean, this is still just a triangle. Isn't this guy going to be half of this guy? And it doesn't look still parallel to it? You keep going forever.
What's the midpoint of the triangle? Like, I thought all those lines.
Well, triangles don't have midpoints. You mean the centroid
No. Like the midpoint.
of this guy?
No, like the big one.
Of this guy? The centroid of that guy?
Oh yeah.
Triangles don't have midpoints. Segments have midpoints. Triangles have centers, but we don't call them midpoints.
Well, centered. That's where's the center.
Well, which center? The centroid?
No.
It's the only center you know is the centroid.
Okay, yeah. That.
So you want to find the centroid of this guy?
Well, I just want to know if it's like.
Well, let's see.
Never mind.
I have no idea, but let's find the centroid. Isn't the centroid the intersection point of the medians?
Yeah.
Okay, let's draw the medians in then. It's right there.
Okay.
Okay, which looks like it might actually, this is very interesting. It looks like that point might be the centroid of the whole big triangle, but it also looks like it might be the centroid of this smaller triangle in the middle, doesn't it? Doesn't this look like the centroid of this triangle right here?
It also looks like the center of the bigger but smaller triangle.
It does. This is getting weird.
That's great.
It does look like that, yeah. Yeah, I bet it is. Yeah, but
It's also a crosshair for where all the other triangles are going to go.
yes. Interesting. This is very interesting. Beard.
Can I get the homework?
Beard. The one who's willing to say, we don't care. Let's just get the work done. I can appreciate that, Beard.
Don't ask the question.
I can appreciate that, Beard. All right. This question here, it's the same thing. Okay, let's just talk about it real fast. Elm Street is supposed to be the mid segment. Okay, so this oak is 1.4 miles, so this is 0.7 miles, and it gives you a path. All right, so you just add up all the lengths, but you're just using this mid segment theorem. All right, if Oak Street's 1.4, then Elm is 0.7, and then just make sure when you go list the streets that you add up all of those appropriate side lengths. There's one homework question, I believe, in the assignment tonight that's just like this, but it's really not that tough. You're just adding a bunch of sides. All right. Notice that this point P to Elm is 1.3, so this is also going to be 1.3, and then it gives you a route. Just add up those appropriate side lengths. Questions about triangle mid-segment theorem? Shouldn't be too bad. Should not be too bad. Here is your assignment. Go ahead and get started. You might even be able to finish. Thanks to Beard.